Design and analysis of mounting arrangement of the rotary turbine control, RTC, drive system. Turbocharger is the turbine-driven force induction device widely used in IC engine applications to meet performance and emission requirement. The rotary turbine control, RTC, system is the invention of Cummins in turbo technology field. The components of system are RTC valve, actuator, and RTC linkage. The RTC linkage contains lever arm and spring and it connects actuator shaft and RTC valve shaft. Actuator rotates valve by using linkage. RTC valve manipulates the exhaust gas going in the turbine housing. This valve is actuated by engine control module, ECM, through the actuator. ECM unit sends signal to actuator depending on the road condition and then actuator rotates valve by using RTC linkage. This paper has two goals. First is to design bracket to support actuator on turbine housing in the given space, claim and validated design of bracket by modal analysis and RVA for given conditions. As all RTC system components are close to turbine housing, so they are exposed to high temperature. The actuator and spring are very temperature sensitive. So, second goal is designing of heat shield for actuator and spring and validate these designs by using steady thermal analysis for given temperature conditions. Keywords: turbocharger, turbine housing, TH, rotary turbine control, RTC, cause and effect matrix, CNE, modal analysis, power spectral density, PSD. Introduction. Cummins Company has many generations of turbocharger. According to recent emission norms, the exhaust gases coming out of engine should be minimum as possible. To meet this condition, Cummins introduces RTC system to automobile industry. RTC valve is placed at the inlet manifold of the turbocharger in the turbine housing SS shown in the 1.1 by red dot. This valve manipulates exhaust gases before going into the turbine housing. The components of RTC system are RTC valve, RTC linkage, and actuator. RTC valve manipulate the exhaust gas. RTC linkage connects valve shaft and actuator rotate valve by using RTC linkage. According to road and engine condition, engine control module, ECM, sends signal to actuator rotate valve through linkage and exhaust gases is manipulated. General principle of RTC valve is as shown in 1.2. RTC valve controls exhaust gases going in the turbine of turbocharger. Using RTC valve, some amount of gas is sent to turbine wheel and some exhaust gas passes straight to the after-treatment system depending on the engine condition. RTC is one of the important inventions in automobile industry that can bypass 100% exhaust gas passes straight to the after-treatment system. 4. High-volume bypass. 2. Problem statement. It contained two parts and they are 1. Design of bracket for the actuator. Actuator is driver of the RTC system is shown in figure 2.1. So, design bracket to support actuator on the turbine housing and validate design. 2. Design of heat shield for actuator and coil spring. The RTC system is close to turbine housing, blue color body in 2.1, and engine, so it will exposed to high temperature. High temperature affects the working of actuator and spring, so design the heat shield for both and validate design. Heat coming to spring and actuator is shown in 2.1. Figure 2.1. Heat coming to actuator and spring. 3. Concept generation for bracket and heat shield. While designing bracket of heat shield of actuator and heat shield of spring, various factors are considered and these are given space, claim, material, cost and surrounding temperature. Few concepts for bracket and both heat shield are explained below. A. Concept A. In this concept, the designed bracket can be manufactured from one blank. The lower part of bracket is act as support of actuator and side wall of bracket act as heat shield for actuator and spring. For mounting of bracket on TH, 5 bolts are used. In 3.1, orange part is a bracket. This is manufactured from bending process. 3.1 Concept A. To protect actuator should be shield from 3 sides, but in this concept the heat shield is for only one side of actuator. This is the drawback of Concept A. B. Concept B. In this concept, the separate heat shield is designed for actuator and spring and bracket for mounting of actuator. Bending process is used for manufacturing of heat shield and bracket. Both bracket and heat shield are mounted on the TH. In 3.2, gray part is heat shield and orange part is bracket. 3.2 Concept B. Drawback of Concept B is that spring is still exposed to the radiation coming from inlet flange of TH shown by arrows in 3.3. 3.3 Radiation coming to spring. C. Concept C. This concept is addition to Concept B. The extra heat shield for spring is designed. In 3.4, pink part is heat shield of spring. 3.4 Concept C. In this concept, for mounting of heat shield of actuator, 4 extra bolts are used shown in 3.4 by circles, which will increase cost. This is the drawback. D. Concept D. The disadvantage of Concept C is removed in this concept, i.e. extra bolts are used for mounting of heat shield are removed. Concept is shown in 3.5. 3.5 Concept D. 4 Concept selection. Concept selection is the process of evaluation concepts. comparing the relative strengths and weaknesses of the concepts and selecting one concept. The concept is finalized by considering factors like space claim, protection of all components of system, cost, and different criteria. Pew matrix and CNE matrix are used concept finalization. A Pew matrix. During concept selection, initially concepts are evaluated relative to a baseline product using the Pew matrix. Pew matrix compares all concepts with baseline and gives best concept from all. For Pew matrix used for the concept selection, refer Table 1 in Appendix. After the rating in Pew matrix, Concept C and Concept D got same rank. To select best concept from these two, CNE matrix is used. BCNE matrix. In this matrix, ratings from 1 to 10 are given for the concepts. One more advantage of this matrix is weightage is also given to the criterions, so we can get more accurate result. In a CNE matrix, customer requirements i.e. criteria are ranked by order of importance to the customer. The CNE matrix is shown in Table 2 in Appendix. The meaning of rating used for comparing concept with baseline is 0 none, 1 weak, 3 moderate, 9 strong. As the concept D got high rating in CNE matrix sheet, so this concept is finalized. V. Design of selected concept. While designing final concept in details, following factors are considered. 1. Available space claim. 2. Material of bracket and heat shield as per surrounding temperature. 3. Overhang reduction of RDC linkage. A. Design of bracket. The actuator having 1 kg mass is mounted on bracket and bracket is fixed on TH using 5 bolts. As grade 304 stainless steel have high tensile strength, so this material is selected for it. As bracket manufactured by bending procedure, so its thickness decided as 3 mm, as thickness of 3 mm of sheet is widely preferred in Cummins, and for manufacturing of sheet having thickness greater than 3 mm, special tools are required which require more cost. The detailed view of bracket is as shown in Figure 5.1. 5.1 Bracket. B. Design of heat shield of actuator. By considering space between turbine housing and actuator, the thickness of this heat shield is selected as 2 mm. The material for heat shield is selected as grade 304 stainless steel because it have good thermal resistance and high melting point. The detailed view of heat shield for actuator is as shown in Figure 5.2. Figure 5.2 Final heat shield for actuator view. C. Design of heat shield of spring. By considering gap between spring and valve side lever arm of RDC linkage, the thickness of this heat shield is selected as 1.5 mm. The material for heat shield is selected as grade 304 stainless steel. The detailed view of heat shield for spring is as shown in Figure 5.3. Figure 5.3 Final view of heat shield for spring. 6. Validation of design. The modal analysis and RVA are performed to check the strength of bracket. Steady thermal analysis is performed to calculate temperature of actuator and spring before and after mounting of heat shield. 1. Modal analysis. Modal analysis examines the modal behavior of model. Modal analysis is used to calculate the natural frequencies and mode shapes of model. The analytical frequency of bracket and heat shield for inline engine is given by below equation. Engine speed 3000 rpm. Number of cylinders of engine 6. Equals 330 Hz. 1.1.1 Geometry details. The assembly of following parts is considered for modal analysis as shown in 6.1. 1 heat shield for spring. 2 bracket. 3 heat shield for actuator. 4 actuator.